introduction. Recording in progress. Okay, I have to click got it. There we go. All right, yeah, so thanks again, Yen. Thanks for the generous introduction. It's great to be here. Yeah, so today I'd like to talk about, okay, so the technical version of the technical title is Low Bandwidth Evaluation of Linear Functions on Reed-Solomon-Encoded Data. That's a bit of a mouthful. So what this talk is actually about is how do we efficiently compute on encoded data, and when would we want to do that? And this is based on joint work with Noah Shetty from Stanford. Okay. Yeah. So what is this talk about? So as you could guess from the subtitle, the talk is about how do we efficiently compute on encoded data. So this phrase could mean a bunch of different things depending on how we define efficiently, compute, and encoded. So the way I'm going to do it for this talk is the following. So efficiently, by efficiently, I'm going to mean with low communication cost. And I'll talk a little bit more about the model in just a moment. By compute, I mean compute some function of your data. In this talk, I'm going to be focused mostly on linear functions, but this question is generally interesting for larger classes of functions. And what do I mean by encoded? I mean encoded with an error correcting code. And in this talk, I'm going to focus on Reed-Solomon codes, but part of the argument is this should be interesting for a whole family of error correcting codes. Okay, so in a bit more detail, let me tell you the outline and also just the main takeaway so that if you zone out after this slide, you know what you're supposed to get out of the talk. So the outline, so first I'm going to give sort of a more formal setup and problem statement of like what I mean by these definitions here. And then I'm going to talk for a little while about where this question comes up, because this question or questions of this flavor have been coming up, or I've just been noticing them more coming up in a wide variety of areas recently. And that's going to lead sort of to the main takeaway of the talk, which is that I think that this and sort of related questions to this are sort of well-motivated questions that we should study systematically. I think it's sort of been cropping up in special cases in a number of different places, and people have been studying those special cases. But I think it'd be really cool to sort of study this question sort of more intentionally and more in a more unified way. So our work takes sort of one step towards this, but there's a lot more to do. So I think that's the main takeaway that I want you to get from the talk, is that this is an interesting question and everyone should study it. Okay, so that's the second part of the outline. The third part is I'll actually tell you about our results, this sort of one step towards understanding this. And we're going to look at, like I said, the special case of linear functions and of Reed-Solomon codes. And time permitting, I'll say a few words about the proof. We'll see how the time management goes. And please do stop me and ask questions at any point. It's very sad that we can't be doing this in person, and yeah, I would love for this to be as interactive as possible. So please stop me. Just unmute yourself and speak up. I'm not sure I can see the chat box with my laptop set up, so just unmute yourself and talk. Great. Okay, so let's get started with the sort of formal setup and problem statement that I want to talk about today. And so I'm going to motivate this loosely by kind of like a stylized example in distributed storage, just so we have something like some concrete application to think about. But as I'll say in a moment, this question is kind of interesting in a variety of different settings. But let's start with distributed storage. So here is a very stylized way that distributed storage actually works in practice. So suppose you have some data, F. So it's a vector of length K over some finite field, capital F. And so throughout the talk, capital F here is going to be some finite field, and think of it as being kind of large. Right? So we have our data, it's this vector of length K, and we want to store it on N storage nodes in some distributed storage system, like you do. So the first thing you would do is just like, okay, here's the data stored on the nodes. But the catch is that we would like to be robust to node failures. So if some node goes down or becomes unavailable, we don't want to lose data. So this is a problem that has been around for a long time. And there's fortunately a classical, very beautiful solution called Reed-Solomon codes. So here's how they work. We're going to fix N points, which I'm going to call evaluation points, alpha 1 through alpha n in my field F. So n is going to be the number of storage nodes. Here, think of n as being larger than k. And these alpha i's should all be distinct. And then I'm going to define a polynomial f of x, where f is just the polynomial whose coefficients are the elements of my data vector here. So it's f0 plus f1x to the 1 plus f2x to the 2, dot, dot, dot. So it's a degree k minus 1 polynomial. All right. Now I'm going to take this polynomial and I'm going to evaluate it on all of those points. And that will give me some vector. N is larger than k, so this vector is going to be longer than my original data. And in coding theory jargon, I'm going to call this vector a code word of my Reed-Solomon code. So it's a vector of length n over this field f, and I'll call it a code word. And now what am I going to do with this code word in the distributed storage context? I'm going to take each symbol, so each one of these evaluation points, and sort of ship it off to a different storage node. Right. Okay, so why would I do this? It turns out that if you do this, this sort of gives you the optimal trade-off between the number of failed nodes you can tolerate and the amount of overhead that you have, like the amount of extra symbols you actually have to store. So let's see why. So suppose that some n minus k nodes fail or become unavailable. So then I have k nodes left. And I claim that no matter which n minus k nodes fail, I actually haven't lost any data. And the reason is because polynomial interpolation, right? Here I have k evaluation points of a degree k minus 1 polynomial. 2 points determine a line, 3 points determine a quadratic, k points determine a degree k minus 1 polynomial. So I do polynomial interpolation, solve some linear system, and I can recover my data. And you can do this no matter which n minus k nodes failed. And it's not too hard to see that this is optimal, right? If I want to get these k symbols back, I need at least k symbols to have survived, just sort of information theoretically. So this is a very strong property that is satisfied, and it's a very nice property. So just some jargon, we call this property maximum distance separable in coding theory. So an MDS code is one that allows you to recover all of your k symbols of data from any k surviving nodes. So Reed-Solomon codes have this property. For this reason, they are actually used in distributed storage. They're used all over the place for a number of different applications. It's a really beautiful classical construction. Are there any questions about this construction, or like Reed-Solomon codes using polynomials to store data this way? Because this is going to be the basis for the rest of the talk. Okay, fantastic. Great. Okay, I'm just going to simplify the picture a little bit. So we're going to get rid of those yellow boxes. But so from now on, I'll draw the picture like this. But yeah, imagine that these different evaluation points are all held by different parties. That's going to be the important thing, or held by different nodes. Okay, so now I can talk a little bit about what is our notion of efficient computation on encoded data, because that's what the talk is about. Right. So the problem we want to solve is the following. So we have our data, it's stored like this, and maybe some nodes become unavailable. Actually, the question is still interesting, even if no nodes aren't available, but we allow for some to be unavailable if necessary. And now some querier shows up. So let's call her Kiana the querier. And she shows up and she has a function she wants to compute of the original data. So phi of f, where phi comes from some function class curly f. So for us, it's going to be linear functions, but you can think of it more generally in any class of functions. But I'm going to think about this class of functions as mapping the data, which is a vector, down to a scalar. So it outputs just a single scalar. Right. Okay, so Kiana wants to compute phi of f. She's going to broadcast to the nodes the identity of phi and the identity of any failed nodes, so that they sort of know who's participating in the function evaluation. And then each one of these nodes sends a message back to the querier. So node j is going to send a message g sub j of stuff, where the message it sends is allowed to depend on the contents of the node, so f of alpha j, that evaluation point, the function phi that Kiana wants to compute, and the identity of the failed nodes I. And each one of these nodes is going to send back a message. And our goal, sort of the goal of, like, our notion of efficient here is going to be communication efficient, in the sense that, oh yeah, sorry, then Kiana should of course be able to compute the function. But so communication efficient here means that we want to just minimize the total number of bits that she has to download. So the total number of bits in all of these messages combined. And I'm going to call that the download bandwidth of the scheme. Right. And we'd like to minimize that. Okay, so that's the problem we'd like to solve. This is kind of the model. I'm going to give this problem a name. Let's call it low bandwidth function evaluation. And so this is the sort of the formal problem we'd like to solve. Make sense? Great. Okay. Oh, sorry. Spoiler. Yeah. So just to make sure it makes sense, maybe get some audience participation. Like, what's the baseline here? What's the naive thing for Kiana to do?
Just decode first.
Exactly. Yeah. So the baseline is that she should just decode all of the data and then compute the function on it, right? So we just said that from any k nodes here, she can recover the data. So do that, contact any k nodes, download all of the information from each of them. So that's a whole field symbol from each of them. Remember, the field size is large here. It needs to have size at least n because I need these n distinct evaluation points. So each field symbol has at least log n bits in it. So she's going to download log n bits from k different nodes, recover the polynomial, compute the function. Great. However, this seems kind of wasteful because the function that she wants is just, the function of evaluation that she wants is just like a single field symbol. And instead, she's downloading enough information to recover all of the data and throwing most of it away. So quantitatively, she's downloading at least k log n bits, whereas she might hope to do a lot better. So the question is, can she do better? And okay, spoiler alert, the answer is yes. So here's a preview of our main result. So we have this same setup, and we allow for any nearly n minus k nodes to be unavailable. So n minus k times 1 minus epsilon for some small constant epsilon. Although again, this is actually, I think, still an interesting question, even if none of the nodes fail. The querier shows up, and we managed to get a scheme for linear functions. So the type of function she wants to compute is what is the inner product of v and f for some query vector v. Okay, so she communicates v and the identity of the failed nodes to these. And then each of these surviving nodes can return just a constant number of bits. So not a whole field symbol, just a constant number of bits to Kiana. Here, constant depends on epsilon in some particular way, but let's just think of epsilon as a constant. And from this, she's going to be able to compute this linear function that she wanted. So this is sort of the main result that we're heading towards. Just some quick notes about this. So first, how does this compare to the naive schemes? The naive scheme needed k log n bits. If k is on the order of n, which it is sort of for these distributed storage schemes, this is saying that the code has constant rate. And in this scheme, Kiana can download only O of k bits instead of k log n bits. So she's saving a factor of log n. And moreover, you can show that this is optimal. Omega of k bits are required. Further note that we can sort of approach the optimal number of failures here. So if more than n minus k nodes fail, then data is actually lost, and there's no way that we could hope to compute any linear function. So n minus k is the max, and we can sort of approach that as epsilon gets small. And just a note, which maybe I should have put this on the slide first, there's actually a simpler version where if there are no failures, a simpler version of the theorem where if there are no failures and k isn't too large, like at most n over 4, then you can replace this big O of 1 with just 1. So just 1 bit per node will allow you to compute any linear function you like, of course, depending on the linear function.
And the constants in this O's, they depend on epsilon.
That's right. Yeah. So the constant in this big O, so this, the fine print down here is that big O of 1 means big O of log 1 over epsilon by epsilon. Yeah. So it depends on epsilon. Right. Yeah. So this is sort of the preview of the main result that we'll get to. So I'll say this, in more detail with some quantifiers later. But are there any other questions about this now? Yeah, so we actually found this result rather surprising. We set out to try to understand oh, surely there are some good linear functions and there are some bad linear functions, like some that we can compute and some that we can't in low bandwidth. It turns out that they're all good, which kind of surprising. Anyways, yeah, so I'll get back to this result and its proof later. But what I wanted to do first, and again, this is getting back to the main point of the talk, is to tell you sort of where this question comes up. Because I think this notion of low bandwidth function evaluation or communication efficient function evaluation on top of error correction, it's kind of an interesting question that's popping up in a bunch of different scenarios, a bunch of different cases recently. I think it's a well-motivated question. Okay, so I've already talked a little bit about the distributed storage setup. I had this stylized example where a querier wants to compute some data of some function of data that's stored in a distributed storage fashion. This has already been studied, or special cases of this have already been studied in the distributed storage literature, in particular in regenerating codes. So the idea with regenerating codes is that your goal is to recover just one missing node. So imagine you have some big data center and a node fails, and what you would like to do is set up a replacement node. and that that replacement node should have exactly the same data on it as the node that went missing did. So this is a special case of this low bandwidth function evaluation, where my class of functions curly f, which happens to be a subset of linear functions, is just a set of all functions which tell me what should that ith symbol be. So in the case of Reed-Solomon codes, what is f of alpha I if I'm not allowed to access that one thing? And it turns out that Reed-Solomon codes are well studied as regenerating codes. So this work was started by a very nice paper of Shanmugam et al. From 2014. And then there's been a long line of work since, which actually shows that Reed-Solomon codes, it can in fact be optimal regenerating codes in many parameter regimes, which is pretty cool. Low bandwidth function evaluation then just sort of generalizes this paradigm and sort of this line of work to general arbitrary to arbitrary functions, or in our case to linear functions. Okay, so that's one case where this comes up. Another sort of different flavored case where questions like this have been coming up recently is in the literature on coded computation or gradient coding. So the basic idea here is, so actually coded computation can refer to a number of different problems, but I'll just describe one of them, which is known as gradient coding. The idea here is that you've got some data and you want to do a distributed computation on it. So no longer distributed storage, but distributed computation. And so let's say your data are like, you have k vectors x, and maybe you want to do distributed gradient descent. So one thing you could do is just do distributed gradient descent. That's fine. But one thing that people have been sort of exploring recently, and I'd point you to this great survey by Leah and Evestimer for an overview of all the exciting stuff that's been happening in this area, because it's a very large area at this point. Yeah, so the basic idea is you have some parameter server. It's going to want to compute the gradient of some loss function on your data at some particular parameter, and then update the parameter. So what are you going to do? One thing you can do is add redundancy to your data. So encode your data using some type of error correcting code, or some type of redundancy adding thing, and then ship this encoded data off to your compute nodes. And then the parameter server says, oh, hey, my current iterate is theta. Each of these compute nodes computes something like a partial gradient at theta or something like that, and returns a message. But the issue is that some of these nodes might be slower than others. So you might have stragglers. And it turns out this actually is kind of a problem if you're trying to do massive distributed gradient computations or gradient descent. And then from the messages that come back, the parameter server is supposed to compute phi of x, which in this case is the gradient of loss, update phi, and continue. So this is sort of like again, a special case of this trying to do low bandwidth computation on top of encoded data if you care about the amount of bandwidth downloaded. And here that your class of functions f is just a class of gradients for various different parameters. Yeah, so just what's been done in this space, there's sort of two lines of work here. One attempts to optimize the download bandwidth, which is sort of what we're trying to do, but uses replication-based code. So basically, they just replicate the data according to some appropriate combinatorial design. And then the goal is to show you that you can tolerate a certain number of stragglers, or maybe that you can speed up the convergence of gradient descent by sort of combining data in particular ways. So there you care about the download bandwidth, but not necessarily the rate of the code. You don't necessarily want it to be a good code. Other works use actually mostly Reed-Solomon based coding. So you care about the rate of the code, you care about the overhead, but they don't care so much about the download bandwidth. Yeah, so in some sense, this notion of low bandwidth function evaluation kind of sits in between those two, is trying to, trying to both have low coding overhead, but then also to download the bandwidth, or to decrease download bandwidth. So that's another case where this flavor of thing has been showing up recently. And then the third example I want to mention is homomorphic secret sharing. This was introduced by Boyle, Gavoy, and Ishai in 2016. And I reference you, or point you to that reference as well as this other paper for more on this field. But the way this works is the following. So again, totally different area. Now I want to do secret sharing. So I have some secret, let's say S0 through SL-1. So it's a length L secret that over some finite field. And I want to share it between n parties. in a way so that no K minus L parties can learn anything about the secret, but any K parties can completely recover the secret. So this is sort of a classic desiderata in secret sharing. And such a thing is useful for all sorts of applications in cryptography. So a classic way to do this is with Shamir's scheme. So Shamir's secret sharing scheme works as follows. I'm going to take my secret, I'm going to pad it with some random bits. So now that I have a vector of length K, and then I'm basically just going to encode that with a Reed-Solomon code and treat my parties as storage nodes like I did in the previous slide. So I'll define some function f whose coefficients are this data and send it off to each of the parties. And if you haven't seen this before, it's not too hard to check for yourself that indeed no K minus L parties can learn anything about these L bits of secret, whereas any K parties, as we saw before, can get together, do polynomial interpolation, and recover the secret. Okay, so far this is just secret sharing. The notion of homomorphic secret sharing, which was introduced much more recently than secret sharing, and which has applications in, for example, private information retrieval and multi-party computation, is that there should be the following guarantee on top of your secret sharing scheme. If you have some referee who comes along who wants to compute a particular function of the secret, they should be able to do it by receiving some compact output shares from each party. And so this is, again, like very similar, just basically exactly the same question as this low bandwidth function evaluation, where your class of functions curly f is the class of functions of this vector that happen to only depend on the secret, or maybe a particular class of functions that you might be interested in for the application. So in particular, our result says something about homomorphic secret sharing scheme for linear functions. Right, yeah, so just, again, some notes. Most constructions for homomorphic secret sharing are in the cryptographic regime, so not the information theoretic regime, so I'm allowed to make crypto assumptions. But in the information theoretic regime, this low bandwidth function evaluation results would imply a low download rate, single client information theoretic HSS for Shamir sharing. Yeah, so I was just running through those examples just to give you a flavor of like all of the different places where let's sort of like computing on top of error correcting codes in a low bandwidth way has been showing up recently. And so once again, the main takeaway that I want to give in this talk is that this notion of low bandwidth function evaluation or very similar notions arise in a bunch of different settings for particular classes of functions curly f and or for particular codes. Reed-Solomon codes are particularly interesting. Yeah, and I just really think there's something to be gained by studying this systematically. So that was really the motivation for this work, is like, okay, let's like take a step back and try to abstract this problem out and see what we can do for the most natural class of functions to start with, which for me would be the linear functions. So that's sort of where we're starting. But of course, there are plenty of other open questions, like can we generalize this to other classes of functions curly f? Can we explore low bandwidth function evaluation in other parameter regimes that are sort of more directly related to these various application settings? And of course, even can we find some other application settings? And can we also unify work that's already been done in these other settings? I think these are all really interesting directions. Are there any questions about that before I then sort of go into a more technical part and tell you about what our results are and how we actually get them? Cool. Okay, so let me tell you then about this result. So here's the picture again. I think this result is just really interesting just from the perspective of like polynomial interpolation. So even if you didn't get my like, or even if you're not compelled by my little soapbox about low bandwidth function evaluation that I just did, surely everyone loves polynomial interpolation. So hopefully this is just interesting from a mathematical perspective. Right, so basically what this is saying is there is a way to, compute linear functions of some polynomial basically in a very low communication way, which I found very surprising. We kind of set out to show that you couldn't do this and then discovered that you could. Okay, yeah, so here's the main result. We'll be able to tolerate a bunch of failed nodes, download a constant number of bits from each surviving node and compute whatever linear function Kiana happens to want. So with some more quantifiers, here's a still simplified version of the theorem. Let's let alpha be greater than gamma be greater than 0. These are some constants. So alpha is going to be the maximum fraction of failures possible. And gamma is going to be the fraction of failures that actually happen. So alpha is going to be like 1 minus the rate of the code, basically. And let's pick a parameter t greater than or equal to 0. Let's let n be equal to q to the t for some sufficiently large q. Right, so q is going to be on the order of 1 over alpha minus gamma. So alpha would be the maximum number of failures we could possibly tolerate, even if we didn't care about low bandwidth stuff, and gamma is the number of failures that we actually have. So this is like, you know, the gap between that. So q has to get larger as that gets close. And so we should think about q as constant, but t is growing with n. That's sort of the parameter regime that I want to think about. Let's let f be a finite field of size q to the t. We'll let k be equal to n times 1 minus alpha. So another way of saying this with some coding theory jargon is we're going to consider the full length Reed-Solomon code of rate 1 minus alpha over the field. If that coding theory jargon doesn't mean anything to you, then it doesn't matter. And then with all of these quantifiers in place, the takeaway of the theorem, or the punchline, is for any function f, or sorry, for any data f, for any linear function phi that you might want to compute of f, for any gamma n failed nodes I, there is some scheme that will recover that function phi of f from the surviving nodes with bandwidth this. So this is big O of k times log 1 over alpha minus gamma. So alpha minus gamma here, again, is like that gap, how many failed nodes we have versus what's the maximum, like absolutely possible, and then divided by that alpha 1 minus gamma again. So this is essentially that k times log 1 over epsilon that I had in the previous slide. Okay, so that's the theorem statement. Yeah, and again, there's a lower bound that omega of k bits are necessary, but the dependence on alpha and gamma is in our lower bound does not match at all. And I think it's a great open question to know what that constant is. Okay, so that's the statement of the result. How does the proof actually work? So in order to do this, I'm going to need to introduce some terminology about finite fields. So from here on, I'm going to be working over a finite field of characteristic 2. It's not so important that the finite field have characteristic 2, but it does need to be an extension field, as the theorem said. Characteristic 2 means that I'm not going to make any sign errors on my slides, and that's the main reason to do that, because plus is the same as minus. All right, so we have a field of size 2 to the t, and I'm going to be looking at a vector space f, right, f is a field of size 2 to the t, but it turns out that that field is also a vector space over f2, just 0, 1. So let's let zeta 1 up through zeta t be a basis for that over f2. Right, it's a vector space, we can pick a basis. So let's do that. Right, I need one notion called the field trace, which will be useful. So the field trace, if you haven't seen it before, is defined as this polynomial. So the trace of x is going to be x plus x squared plus dot 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 plus x to the 2 to the t minus 1. And this is kind of a magical polynomial if you haven't seen it before. And in particular, it satisfies the following very useful facts. So the first fact is that it's an f2 linear function, meaning that trace of x plus y is equal to trace of x plus trace of y, which is, of course, generally not true for polynomials, but happens to be true for this polynomial over fields of characteristic 2. And moreover, the trace always outputs 0 or 1, right? So it takes in elements from this very large field of size 2 to the t, but it's always going to spit out either a 0 or a 1. So it's this nice f2 linear function that maps f down to f2. And moreover, it has the property that for any x in my field, if I take the bits trace of zeta I times x, where zeta I are these basis elements, and I look at all of the ones over all I and t, that determines x. So basically, you could kind of think about trace as like taking an inner product or something. So basically what this is doing is just writing x in that basis, x1 through xt. So this is sort of how you write x in that basis. Okay, so that's some technical stuff. I'll put reminders as that comes up, but we'll need this sort of ability to do linear algebra in extension fields. Okay, so now we have our Reed-Solomon code, which is a subspace of f to the n. Right, and so I've already defined the Reed-Solomon code, but I'll just define it again. So the Reed-Solomon code is the set of all vectors f of alpha 1 dot dot up to f of alpha n, where f is some low degree polynomial. So it's the set of all possible code words is what I would call the code. And it's a not too hard to see that this is an f linear subspace that lives in f to the n. So some subspace of vectors over big F of length n. Right, so I'll draw it like that. Here's my Reed-Solomon code. It's a subspace. So because it's a subspace, I can define the dual space, which is just the set of all vectors that are orthogonal to everything in that subspace. So I'll call that RS perp. Yeah, and I'm just writing out the definition there, and I'll sort of draw it like this. So just the standard notion of a dual space. Great. Okay, so now that we have that sort of linear algebra definitions out of the way, let me talk about the proof overview here. So the first step is that we'll come up with a framework that works for any linear code. And then the second step is that we're going to instantiate this framework for Reed-Solomon-Encoded specifically. So let me start with a framework for any linear codes. This will give us a framework to compute any linear function that we want in a low bandwidth way, assuming we can come up with some magical things. And then I'll show you for Reed-Solomon-Encodes how to come up with these magical things. So here's the framework. So this works for any linear code. I'm going to just state it for Reed-Solomon-Encodes just because that's what I've been talking about so far. But this will actually work for any linear code. But by linear code, I just mean any way of encoding the data, going from a message to a longer code word so that function is linear. But I'm going to do it for Reed-Solomon-Encodes. Right. So our goal is to compute phi of f, which is just this inner product v of f, given access to these function evaluations, to these polynomial evaluations. So for simplicity, let's assume that there are no failed nodes, and let's assume that we're trying to download just 1 bit per node. And I'll show you like how we would design a scheme to do this if we want to do just this simple thing. And dealing with failures and downloading more bits per node if necessary is sort of a tedious extension, but the main ideas are all here in this simple case. So an equivalent goal is to compute a linear function of the code word C, right? So this vector f of alpha 1 dot 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 up to f of alpha n, I can call this C, that's my code word. And computing a linear function of the coefficients is the same thing as computing some possibly different linear function of the code word, because everything inside is linear. So it's going to be easier to reparameterize. So I'm going to now be thinking of wanting to compute some linear function of the code word or just some linear combination of these function evaluations. So note that W depends on V, but is not unique. There are many different Ws that will give you the same answer here. Okay, so our strategy is the following. We're going to define some good subspaces. And so what does good mean? I'm going to define some F2 linear subspaces, W1 up through Wn in F. So remember, F is a vector space over F2. So it makes sense to talk about subspaces of F. And these subspaces are going to have the following properties. So first, they're all going to have codimension 1, meaning that they have dimension t minus 1, because F is a vector space of dimension t. Remember, it has size 2 to the t. And they're also going to have this property, that this is sort of a special property, that for any polynomial of degree strictly less than k, if all of the evaluation points f of alpha j lie in wj for all j, then the function that I'm trying to compute phi of f should be equal to 0. So the picture looks like this. I have here on the x-axis, I've drawn f, and on the y-axis, I also have f. And here's my evaluation points, alpha 1 up through alpha n. And for each one of these evaluation points, I have like a special subspace of f. So like W1 would be all these points, let's say, on the y-axis. Of course, they don't need to be contiguous, and contiguous doesn't even make sense in F2 to the t. I'm just drawing them that way. Yeah, the fact that the dimension is t minus 1 means that these wi's each take up like half of f. And now you can say, okay, like what sorts of polynomials go through all of these subspaces, right? Like what sorts of polynomials have f of alpha j in wj for all j? So maybe like this one satisfies that, or so does that one. Like maybe there are a lot of low degree polynomials that interpolate through these subspaces wj. What my requirement here says is that any such polynomial that does that needs to have the property that phi of f is equal to 0. Okay, so there might be many different polynomials that do this, but they should all have the property that phi of f is equal to 0. And I claim that if you can come up with such subspaces, then we can achieve our goal of computing this linear function of our data by downloading 1 bit per node. So how does that work? Oops, I'm sorry, I don't know what happened there. basically the scheme is just going to be that node J, so the node that's holding f of alpha J, it needs to send one bit to Kiana. And what bit is it going to send? It's going to send 1 if f of alpha J is in Wj and 0 otherwise. Right, so it's just going to say, do I live in Wj or not? And suppose that there are sort of two possible answers that Kiana, the querier, is trying to decide between. Like either the answer is going to be phi of f or it's going to be phi of g. And if those two answers are different, then because phi is a linear function, that means that phi of f minus g is not equal to 0. In particular, what sort of the contrapositive of this statement here implies is that there must be some wj so that f minus g of alpha j does not live in wj. Right, so phi of f minus j is not equal to 0. We just said that if you're a polynomial and you go through all these subspaces, then you better have phi equal to 0. So if phi is not equal to 0 for this polynomial, there must be some j so it doesn't go through this subspace. Right. But in that case, and here we're using the fact that we're in a field of characteristic 2 and the dimension is t minus 1. It either has to be the case that f of alpha j is in wj, but g of alpha j is not, or the other way around. If they were both in wj, then their difference would be in wj. And if they were both not in wj, then again, their difference would be in wj because they'd be in the same coset. Right, so that means in particular that we can tell phi of f and phi of g apart, because in this case, node j would say 1, and in this case, node j would say 0. So that means that the responses that Kiana is getting are going to be different in those two cases. So that means that whenever phi of f is not equal to phi of g, the querier can tell the difference from queries that look like this. Does that make sense? Okay, so right, okay, so this says all we need to do is come up with some subspaces that have this property for any low degree polynomial. Of course, it doesn't tell you at all how to come up with those subspaces, and that's kind of the tricky part. But so here's sort of the framework. We just need to come up with these subspaces. But then what the heck are they? So in order to understand how to do that, let me reformulate this goal a little bit using maybe some of the jargon that we saw earlier. So we want to come up with a bunch of subspaces so that for any low degree polynomial, if that low degree polynomial goes through all those subspaces, then phi of f better be 0. Another way to say that is that for any code word C in my Reed-Solomon code, so remember just any vector of low evaluations, if C lives in W1 cross ... cross Wn, which is exactly the same as saying if f of alpha j is in Wj for all j, then the inner product of C with W better be 0. That's because that's like the definition of phi of f is just this linear function. So just translating that, and then I can translate that again. That's basically saying that W needs to be orthogonal to the span of the Reed-Solomon code, intersect W1 cross ... cross Wn. So again, why is that? Basically, yeah, what is this saying? This is saying for any vector C that lives both in my Reed-Solomon code and in this space of subspaces here, right? So AKA any code word that lives in this intersection, it better be orthogonal to W. That's the same thing as saying that W better be orthogonal to the span of this intersection. So sorry, this is a bunch of, I know that was maybe a lot of symbols, but the whole point is to get to this thing now. So if you sort of zoned out with that, come back, and the whole point, the takeaway here is that if it is the case that you can come up with some W's, so that some capital W's, these subspaces, so that little w is orthogonal to this, then we win and we can compute the linear function that's defined by little w. So this is going to be our goal. Right, so that's sort of the framework for any linear code. Oops, we just want to come up with these capital W's that play nice with whatever W we actually want to compute. And now in the remaining, I don't know, maybe 10 minutes or so, let me give you some idea of how we actually can come up with those subspaces W, because there's sort of some nice geometric intuition there. So I'll do that next. Are there any questions at this point?
So are we going to be able to efficiently compute those subspaces?
Yes, yes, yeah. So great question. Yeah, so it turns out these subspaces, in the paper, we have like a very explicit description of these subspaces in terms of the polynomial. And I didn't say it when I was sort of describing this scheme, but I guess the messages are easy to compute. They're just 0 or 1, but also the reconstruction algorithm is also super efficient. It's basically just doing some linear algebra. Yeah, so everything is completely explicit and efficient. Yeah, good question. Any more questions at this point? Cool. Okay, so let's come up with, let me at least wave my hands a little bit at how to come up with these subspaces W, or at least like why they're challenging to come up with. Right, so in order to describe this in 10 minutes, I'm going to lower the bar a little bit. So our original goal here was like, you give me a W and I compute this linear function that depends on W. I'm going to lower the bar somewhat and just say, let's just do this for any non-trivial W. Just even one of them will be fine. And it turns out that basically the ideas in there are enough to do it for any particular W you want. So what do I mean by non-trivial? So a trivial W would be W that lives in RS perp, that lives in the dual code, because then phi of f, which is defined this way, right? It's the inner product of W and the code word is going to be identically 0. So that would be trivial if you asked me to compute a linear function that's given by a dual code word, because I would just say 0. But for anything else, let's just try to come up with something, right? So here's sort of the geometry of what that looks like. Remember, our goal was this, like if we can come up with some, so now we also get to design W too, because we've lowered the bar so much. So now we just want to come up with this little W and these capital W's so that little W is orthogonal to this span. If that happens, then we win. And I claim that it's enough to find WJs so that the dimension of this intersection, or the dimension of the span of this intersection, is less than the dimension of the Reed-Solomon-Encoded. And let's see why. So like ideally the picture would look like this, right? Here's my Reed-Solomon code. It's this subspace thing. Here's this, the dual space, which is, remember, this is where all the trivial W's live. And suppose that it were the case that the intersection of the Reed-Solomon code with, I'm going to call this W1 cross Wn, I'm going to call that curly W. Suppose it were the case that the intersection of the Reed-Solomon code with curly W looked something like that. And this is not meant to be a dashed line just because I like dashed lines in PowerPoint. This is meant to be like, it's not the entire line, right? This is not necessarily a linear subspace or anything like that. But suppose that it happens to be contained in a linear subspace, right? Then when I take the span of this intersection, what I get is this green line here. Right, so this would be the span of the intersection of the Reed-Solomon code with W, which was sort of this purple thing here. And in this picture now, the dimension has been reduced. I went from having a plane to having a line. And I claim that that will allow us to find some non-trivial W, because now there's sort of enough space. Like I have enough space to find some W that's orthogonal to this span, but doesn't live in RS perp. So to illustrate why this is sort of necessary, like what could go wrong, let's just remember that elements of the Reed-Solomon code intersect this curly W. They look like this, like f of alpha 1 should live in W1, f of alpha 2 should live in W2, and so on. These are not linear constraints. There's no reason that this intersection needs to be a linear subspace. So like it could look like this, right? The picture could look like this, where I have my Reed-Solomon code and this intersection is just some weirdo nonlinear set. And then when I take the span, nothing changes. Right, so the span of the Reed-Solomon code intersect this curly W is just the whole thing again. And if that happens, then I sort of have no space to come up with a non-trivial W here. Any non-trivial W that's orthogonal to this thing is going to live in the dual code, and that was only a trivial W. So there are no non-trivial Ws if this is the case. So what I really want to happen is this picture, that when I take this intersection, I happen to have knocked down the dimension a little bit. Right, and so the challenge here is that, right, we want to knock down the linear dimension, but we don't have linear constraints. Like what we have are these constraints. These are F2 linear constraints, but they're not linear constraints over the big field. And so the challenge is we need to turn constraints like f of alpha j lives in wj into a non-trivial F linear constraint, so a linear constraint over the big field. And these are not necessarily linear. So how do we do that? How do we get F linear constraints? So the basic idea is the following. I'm going to write, and here's where that trace jargon comes in. I'm going to write wj as the set of all x's so that the trace of x times some pj that I get to define is equal to 0. This is a generic way of writing a codimension 1 subspace in an extension field. So just believe me if that's not, if you're not familiar with the trace function. But so I can write my wj like this. And now I'm going to define a polynomial, polynomials everywhere, p of x, so that if I evaluate p on alpha j, I get this particular pj. And so I haven't picked the pj's yet, so I haven't picked p of x yet. But basically, I'm trying to turn the problem of picking the wj's into the problem of picking a nice polynomial, because I know how to think about polynomials. Okay. So let's define this polynomial that's connected to the wj's in this way. And then we can look at the polynomial r of x, which is the trace of p of x times f of x mod x to the 2 to the t minus x. Okay, why would I do this? I claim that this polynomial r of x is identically equal to 0 if f is in this intersection, right? So we're trying to understand, like, what is this intersection and is it low dimensional? And so why is this function identically 0? Well, for all j and n, r of alpha j is by definition equal to the trace of p of alpha j times f of alpha j, which is equal to the trace of pj times f of alpha j. But if f of alpha j lives in wj, and wj is defined precisely as all of the things so that that vanishes, then this is going to vanish. Right? So that means that r of x vanishes on all of my evaluation points. So in particular, when I take it mod, this is sort of mod the product of all of the evaluation points, I'm going to get an identically 0 polynomial. Okay. So on the one hand, I have this polynomial that is identically 0. On the other hand, I can just like it's ugly, but I can just write it out, right? I have some expression for p in terms of these coefficients pj, and I have some expression for f in terms of its coefficients. And so I can just, I know what the trace function is. It's some explicit polynomial. So I can just write this thing out. And what I'm going to get is that this is some polynomial of degree at most 2 to the t minus 1. And it has some coefficients. And these coefficients are gross. But they depend on f. And if these coefficients happen to depend on f in a capital F linear way, then we've got an F linear constraint. And so I'm not going to go into the details because it's a huge mess to write down what this stuff actually is. But it turns out that if you do it right, you can write this down so that this stuff is actually a linear function of the coefficients that you're after. And then you know that this stuff must be equal to 0 because this polynomial is identically equal to 0. So that's sort of the main trick. I had an example, but I'm going to skip it because it's gross. Yeah, so just to recap, basically, we just said that we can recover phi of f provided that this condition holds, that w is orthogonal to the span of this intersection. And in order to understand that span, we need to understand like the linear structure of this thing, which is just kind of a weird thing. But in order to do that, we define this other polynomial, show that it's identically 0, and then that means that its coefficients need to be identically 0, and we can use that fact to sort of extract linear constraints that define this span. So that sort of would tell you how to get some non-trivial w, and by sort of reverse engineering this connection, it turns out you can sort of get any w you want out of this, but it's again a little bit messy, so I'm not going to talk about it. Well, okay, yeah. So let me just return to the picture then, because that was just a bunch of math. Again, the main result here is that you can compute any linear function you want on top of Reed-Solomon codes. This has a bunch of different applications, for example, in homomorphic secret sharing, in coded computation, or in distributed storage. And I also just think it's kind of a cool, surprising fact about polynomial interpolation. I like polynomial interpolation. Cool. Okay, so let me just sort of conclude quickly, and then I can take questions. So just quick summary, what did we just see? Right, so we defined low bandwidth function evaluation sort of as something according to this picture. I argued that this shows up in a bunch of different places and we should study it systematically. And that was the main takeaway of the talk. So if you zoned out after that, it doesn't matter, that was the point. However, we sort of made a start at this, at sort of studying this in a systematic way by picking our favorite code, which is Reed-Solomon codes, and looking at linear functions, which seems to me to be sort of like the first class of functions one should look at. We developed this general framework where all you need is for W to be orthogonal to the span of some, particular intersection. This actually works for any linear codes. And then for Reed-Solomon codes in particular, we can sort of find such subspaces by doing some stuff with polynomials. So that's the basic overview. And once again, the main takeaway is, I think this question is interesting and we should study it. Oh yeah, so there are plenty of open questions because that is the main takeaway, is to study some open questions. For example, extending our result to other codes, or even designing codes specifically for this purpose. Extending it to other families of functions. I think low degree polynomials are the natural next thing to look at. If we can get matching upper and lower bounds in the best bandwidth necessary. So the dependence on K is correct, but the dependence on this like alpha and gamma parameter is just like totally not right. Yeah, can we do better by amortizing over multiple functions, evaluations? And one in particular that I'm interested in is what is this good for? So I gave you 3 examples of areas where I think this is good for something, but it feels like it feels like a general paradigm, general question, and I would love to find some applications for it. Okay, so that's it. I'll stop talking now and take any questions. Thanks for listening.
Let's thank Mary. Are there any questions?
I have a question. Can we do something better than just decoding in the case of errors and not erasures?
Yeah, that's a great question. I think you should be able to, in the sense that like for regenerating codes for Reed-Solomon codes, so those are the ones where you just want to, where the particular function you want to compute is just like, what is the missing evaluation symbol? There has been work showing how to do something with errors. Our scheme does not tolerate errors at all. So yeah, I feel like something should be possible, but right now, yeah, we can't do that. Yeah.
Okay.
But yeah, I think that is a good question and very well motivated.
Any other questions? I guess if not, let's thank Mary again.
Thanks everyone for listening to what I realize in retrospect is a rather technical talk at the end of the day. But
thank you. It was very interesting. We are a little bit tired. It is the end of the day for us, but
me too. It's almost 10 p.m. here, so or it's 9:30 here. So yeah.
Right.
Cool. All right. Yeah, but there's something in the chat. I don't know if how long that's been there, but I can't.
Thank you for the. Vladimir says thank you for the great talk.
Yeah, thanks for coming. Cool, and yeah, and thanks again for the invitation. This was fun.
Great. Yeah, thank you. And sorry we couldn't do it in person. So this concludes our sessions for today, and tomorrow we have the last day of CSR. So it starts a little bit later than today, but and I cannot tell you what time your time